going to be talking about so-called fractal potentials of the Laplace and wave equations. So this is going to include my original construction and also expanded to some new differential equations. So I'm currently a postdoc at York University and question? So just to roughly outline my talk, so first of all I'll roughly review what I mean by IFS fractal. So it will be like a reduced definition for the purpose of this construction and invariant measures. So I'll introduce the fractal potentials construction through fractal potential flows, which is probably the most intuitive and my original construction. So you will get an idea of what's going on and why. Why it's done that way. And then sort of show you some plots so you get an intuitive feel that okay, we really have convergence. This is not just questionable thing, and then I'll generalize the construction to other PDEs and give you some technical details of what exactly needs to be done. So this is based on work I did in my PhD thesis. It's an extension of that work. So I already have this first paper online. Did I switch off? Okay. Yeah, I already have this one online. So I mean, this whole construction was designed to be a model for fully developed turbulence. So actually, I don't have any slides on that, so I'm not sure how much familiarity you have about turbulence or fully developed turbulence. Basically, fully developed turbulence means that turbulence at a high Reynolds number reaches stochastically steady state. So not fully steady, but just stochastically. So in a way, you know, that sort of corresponds to the fact that these contractive transforms have an attractor, right, which is invariant. So anyway, the full reasoning is included in the paper, which I'm not going to talk about. I'll just talk about the math now. So fractal potentials of the Laplace and wave equations, same title as my talk, will be the upcoming paper. So I'll be on vacation for 3 weeks now, so I'll be title this up. Okay, so outline of my talk. So first I'll just give some preliminary definitions. And then I'll go into fractal potentials, talk about the main idea of character, which leads to actually a boundary condition, or actually it's another word for the boundary condition at infinity. And then talk about the generalization to the 3D, and actually n-dimensional Laplace equation is also possible, and the wave equation. So what do I mean by IFS fractals here? What I mean is we have this system of similitude contractions. So the pk here is it denotes the fixed point, and the phi k is either just a complex number, which is a contraction factor, or it's a contractive lambda times a rotation matrix. And then we just define a so-called Hutchinson operator or IFS operator, which is the union of the actions. And then Hutchinson has this fundamental theorem that this operator over compact sets in a Hausdorff metric, which form a complete space, is going to have a unique attractor. This is just based on usual technique. So another important definition is the idea of generating addresses. So representing the fractal points with addresses. So typically we start a generation from some C, typically one of the fixed points here. Also, generation on a computer. And then we can have finite or even infinite addresses. So the full address set is a combination of that. So again, the zero address is just corresponds to the identity. Okay. So visually, what this means is that U order is union. So it's the union of two actions, right? So as you take these union of contractions, repeated iteratively, you will arrive at an IFS fractal. So actually, it's important to visually understand what similitudes do. So basically, they have trajectories. So if you have no rotation or factor, or actually your rotation is the identity, then your trajectories will be just straight lines, right? But when you do have a rotation, non-identity rotation, then you'll be following logarithmic spirals. So that sort of corresponds to the idea of an eddy in fluid dynamics. Sorry. Yeah. Okay, so a huge variety of such IFS fractals is possible. So if you consider even just two maps, you can have connected IFS fractals or disconnected or whatever. But as you increase the number of maps, or actually leave the number of maps variable, then you can approximate any complex set through the inverse problem, right? So into IFS fractals ties in the idea of an invariant measure. So if you define a metric or a distance concept between probability measures this way, it will be a metric, and actually probability measures will form a complete metric space with this metric. So if we denote the mapping for the push forward transfer, corresponding basically corresponds to the action of one of the contraction maps, except this time for measures. So this is acting on the measure itself. So basically you could even remove the S from this definition, and then you would say that it's nu composed with dk inverse, right? And if you combine the actions and add some weighting, or you can call them probabilities, then you get this operator, which is going to be contractive over probability measures and has a unique fixed point. It's called the invariant measure. Right? So it all comes out of Hutchinson's original paper, and probably inspired by quite a bit of earlier work as well. So the main idea in trying to take this formalism to potential flows is to link probability measures to stream functions somehow, and to show the existence of the unique existence of an invariant flow. Okay, so I'll just show you the picture first, and then it will give you an intuitive idea. So I'm not sure how well you can see, but for the most important thing, I should have zoomed out a little bit, but the most important thing is that if you zoom out, this whole singular set will reduce to a point, and the stream lines will form an eddy as you zoom out a lot. And that's actually the concept of so-called character or boundary condition at infinity. So and that's preserved with iteration. Right? So whatever the iteration will be defined here, don't worry about what it will be yet, but basically this character is preserved, and so the space of stream functions we are working over will have this character characterizing them. Okay? So you can kind of see that, so I think this is the 8th and 9th iteration, whatever, and this is the, maybe I think that's 5th, I think. So anyway, but for higher iterations you can see that you will have convergence, right? So the set of singularities or eddy centers is going to be an IFS fractal. So as I said earlier, if you increase the number of maps, then you can approach any compact set, and that's kind of an important idea because Mandelbrot did quite a bit of work on turbulence as well, and he has a sort of a conjecture, but it's a scientific conjecture that the dissipation set of a turbulent flow, or sorry, fully turbulent flow, fully developed turbulence, is, so the dissipation set is concentrated in a set of non-integer dimension. So meaning it's a fractal. And that's true for these flows as well. And in fact, through the corresponding inverse problem, we can represent probably a large class of turbulent flows with these kinds of fractal potential functions. So the main idea is that of invariance. So the eddy stream function looks like this. Okay, it's defined over complex number z, and you have the argument function here superposed with logarithm. So what this represents, so the level curves of this stream function will be logarithmic spirals. And there will be a complex branch of this because of the argument function. Okay? So the invariance under an IFS map of this form is actually just an algebraic simple proof. If you define C this way, for that phi, if you define C this way, C here, then we'll have that the stream function is constant along the trajectory of this T IFS map. Okay, and so basically, in particular, for T equals -1, so we have that if we define the push forward again this way, then we will have that this psi is fixed function, fixed point of the T star push forward. So idea one is that maybe this stream function is the attractor of T star in an appropriate function space. Idea two is that maybe we can save a lot of work in trying to show or trying to figure out this function space and showing convergence and all that. Maybe we can save us a lot of effort by figuring out a bijective correspondence between probability measures and potentials. And this will happen through Poisson's equation, right? Because you remember that probably that Poisson's equation links density functions, which are correspond to probability measures. So it links density functions to functions which are the solutions of Poisson's equation. So if we can do that, then we have an invariant. We can show an invariant flow based on the invariant measure. Okay. Let's skip to here. Okay. Yeah. So in order to show bijectivity, using partial differential equation like Poisson's equation, we need a good boundary condition, right, which will ensure resistance of the solution and uniqueness as well. So I'll do this with a boundary condition at infinity, which is basically the idea of character. So it just says what I explained earlier, that the global shape is an eddy. So if we take basically any center of reference, it doesn't matter what we take, and any sequence of complex points going to a complex infinity, then this limit needs to exist. So what does this do? All this does is basically it gets rid of all this stuff and gives us back C. So it's a way to extract C, right? So if we have this eddy which already satisfies our idea of this eddy shape at infinity, then obviously we need to match all other steam functions considered to that character, which is character C. You know what I mean? So basically we are matching our class of functions to the simple eddy in shape, in global shape. Okay? And we need a boundary condition at infinity because we have a contractive mapping drawing everything in, right? So the push forward is drawing in the whole flow field. So yeah, so the boundary condition needs to be at infinity. Okay, so this is the actual theorem which ensures correspondence between flows and densities, or probability measures. So taking any density function, there exists exactly one steam function which satisfies the boundary condition at infinity with this C, which is a bounded function and twice continuously differentiable almost everywhere. Only almost everywhere because when you work, so this is the velocity function, but when you work with steam functions, you always have branch cuts, which are kind of ugly, but you can discard them when it comes to visualization. And it's explained in my paper now. So uniqueness is up to a gradient almost everywhere. So why is that still good? Because what we are actually interested in is just the velocity field, right? We don't actually care about the steam function. So if we only have uniqueness up to a gradient almost everywhere, it's still good because the gradient is the velocity, right? So, okay, so now this slide explains how to define the flow space. And the key idea is measure map, which links steam functions to probability measures. So we need to have an IFS which generates IFS fractal with Lebesgue measure 0. So we cannot have, connected IFS fractals, and we need to have that the imaginary part of C is not 0. So anyway, this is the way we define it, and you can see that we have the Laplacian in here. How many more minutes do I have? Like 10 minutes?
When did you start?
I'm not sure, like 5 or 10 hours?
It's 5:26.
Okay. So we define the class of steam functions this way. So again, we have this boundedness, and we take the metric from the metric on measures. So this will only be a pseudo-metric, so we need to quotient out the equivalence classes, and then we will have a metric space, and it will still be complete. And we can actually nicely show that the measure map is actually a bijective isometry, or isometric isomorphism, and it commutes with the transfer operator. Okay? So these are just some technical properties that are necessary. So the invariant flow can be shown rather quickly from here because we already have the property of a unique fixed point for measures, and then we can transfer everything over with this measurement. Right? So we'll have a unique existence over the equivalence classes, which means that we have uniqueness up to a gradient almost everywhere. So we also have that the singularities, meaning the centers of the small eddies, will lie on an IFS fractal because you can show this property, the limit taken in the earlier metric on the previous page. So yeah, with the associated weightings. Okay, so how to construct these fractal potentials in general, or how to generalize them. So the challenging part is, taking linear homogeneous PDE, the fundamental solution, and even, defining the push forward and the weighted transfer operator appropriately is a challenge because you have to sort of foresee all the technical parts which need to be satisfied, and probably the most challenging part is defining the boundary condition at infinity. And actually, for like the wave equation, it's quite a bit of technical stuff. But and then demonstrate the existence and uniqueness of the solution with that boundary condition. Using your homogeneous PDE. And the standard part is, just based on everything you have already, you can introduce the measure map, show that it's bijective isometry and all these earlier properties, and define a function space, show the existence and uniqueness of an invariant function. So everything is standard from then on. Okay, so Laplace's equation in 3 dimension would look something like that, and the fundamental solution is of this form. So obviously the value you need to isolate here is the QC. So this is the technical thing that will isolate it. So this is actually the condition for the boundary condition at infinity, and we'll need to modify the push forward transverse definition a little bit, and then we can define the weighted transfer. And then we will have correspondence and uniqueness is up to a gradient almost everywhere again for the solution, which is good enough for us. Now for the wave equation, it's a whole different matter because you have time differentiation as well here. And I mean, if you had a plus here, that would still make things nice, but you have a minus, so that's a hyperbolic definition. So this is what the fundamental solution looks like. It actually involves a Dirac delta. So in the boundary condition, you will have to take integrals to sort of eliminate that Dirac delta and stuff. And the initial condition will be just that. And the actual proof for the theorem here, for the unique correspondence, unique correspondence between potentials and densities, actually involves an energy technique. So an energy technique is sort of a standard way to show unique existence of solutions, but here it requires a little bit of tweaking relative to techniques I have looked at in the literature. So the definition of the transfer operator will be not a complete rotation in space-time, rotation and contraction, but you will need to separate the spatial and the time contractions. So just to sort of review what I talked about is, so I've introduced IFS fractals and invariant measures, gave a general framework for constructive constructing fractal potentials and talked about the visual, more intuitive side to it all, and gave the initial boundary conditions necessary for constructing fractal potentials of these more general Laplace and wave equations. For the definition. Any questions? Okay, so thank you. Then we are